Alright, welcome to the second session of the second module, which is focused on, we have so far understood on fabrication. Now we will look into the layout. So, or in other words, we will understand the layout design. So to go ahead, or the layout design rules, which is in turn related with the layout. So let me first begin with the layout design rules. So before understanding the layout design rule, let me first introduce you of how to draw a schematic like this for any of the gate. For example, you have a series of steps. For example, the first step here is to write the symbolic representation. So what is the symbolic representation of a NAND gate? What is the symbol? This is the symbol. So you have a 2-input NAND gate. The two inputs are A and B. Y is equal to AB bar. Y is equal to AB bar. This is the first step. Second step is the truth table. So we will analyze the truth table here. When you look into this, you have A and B, and the conditions are 0, 0, 0, 1, 1, 0 and 1, 1. What is output? 0 into 0 is 0, 0 bar 1. 0 into 1 is 0, 0 bar is 1, 1. 1 into 1 is 0, 1 into 1 is 1, 1 bar is 0. So this is my output Y. This is my output Y, and now looking into these conditions, we have to write equations. I want to finally get a diagram like this, which is called as a schematic. This is called as a symbolic. So without understanding, you people will not be knowing how this is got. So the first step for us is this. Ultimately our goal is this. So this is the first step, this is the second step, and third step we will understand it right now. Truth table condition was when the inputs are 0, the output was 1. When the output or the input is 1 and 0 or 0 and 1, 0 bar 1 and 1. When both are 1 and 1, the output was 0. Now one ground rule, as we have understood in the topic called as pass transistor. NMOS passes logic 1. NMOS passes 0 logic and degrades 1. This is the rule as observed by the scientists. In what way? They say when you have 0 logic for your NMOS, it is excellently 0. But when you give VDD to be passed in the pass transistor like this, if this is your pass transistor, this is your gate, this is your source, this is your drain. When you give 0 logic, how do we give 0 logic? 0 logic is given by this ground. Okay, by grounding the source terminal. What is the output you expect? The output you expect is also 0, or in other words, it is nothing but 0 volts. If suppose you have same diagram given to, provided the gate should be 1, provided the gate should be 1, where it is going to latch close, and as a whole this is on. Now if this source is given to VDD, what is VDD? VDD is logic 1 symbol. Logic 1 symbol. And at the drain we expect the output to be VDD. But since the gate is 1, it is closed, there is some potential at this place called as the threshold voltage, VTN. Therefore, logic 1 will not be completely logic 1. It will not be logic 1. No, it is not equal to VDD. Instead, it is equal to VDD minus VTN. Therefore, we call this as degraded logic. We call this as degraded one. Therefore, what is the conclusion based on the two experiments? NMOS passes logic 0 and degrades logic 1. And in complementary to this, the same rule holds good. PMOS passes, okay, let me change the color. PMOS passes logic 1. PMOS passes logic 1 and degrades logic 0. Therefore, what do we say? In PMOS, if you give VDD, it will be VDD. Where you give 0, it is not 0. It is instead, it is VTP. But what is VTP? In other words, it is negative. So, it will not be 0. There will be a small negative voltage which is called as VTP. Therefore, these are the two conclusions. NMOS passes logic 0 and PMOS passes logic 1. Now looking into this truth table, what is the conclusion? We do 0 has to be analyzed in NMOS and PMOS has to be analyzed in. So 0 logic, since 0 is good for NMOS, 0 logic is analyzed in NMOS and 1 logic is analyzed in PMOS. So based on this, we will go ahead. I'll write it again here. 0, 0, 0, 1, 1, 0, 1, 1. The output was 0 into 0 is 0, 0 bar is 1, 1 into 0 is 0, 1, 1 and 0. So, we will now analyze for logic 0. How can we write? We can write it as SOP form only. Irrespective of any gate, whatever it is, you have to write it as SOP. So, what is 0 here? What is the representation? This is your A and this is your B and this is your Y. Both are 1. 0 is called as AB. Similarly, let me write 1. So the grouping is done with respective to these outputs. So 0 can be now understood as, if this is 1, what is the representation of input A and B? They are 0 and 0, therefore it can be analyzed as A bar, B bar. And as I have told you, you have to represent it in SOP form. You have to represent it in SOP form. So the first one is represented sum of products. So one product I have. The next term will be a sum. So one is A bar and B bar. What would be the next? This is A bar and this is B. So the next term is A bar and B. Likewise, what is the third term? A, B bar. You don't have the last term because it is equal to 0. We don't want this, belongs to a different group. Our focus is only on one logic which is having these three equations, and each of the literals here are represented as A bar, B bar, A bar, B, A, B bar. Now simplify this expression. If I simplify this expression, this was A bar, this is called as B bar plus B plus A, B bar. This B and B bar as per the Boolean laws is equal to 1. Therefore, this is equal to A bar plus A, B bar. Or in other words, A plus A, B bar. This is also as per the Boolean laws. Therefore, this is equal to A bar plus B bar. So what is this? This is here logic 1 representation, which has to be analyzed in PMOS, which has to be analyzed in PMOS. And this is your logic 0, which has to be analyzed in NMOS. Okay. Now what is our 0? 0 is equal to AB, 1 is equal to A bar, B bar. A bar plus. So we'll write here 0 is equal to AB and 1 is equal to A bar plus B bar. So how do we represent? One thing, what is 0? 0 is NMOS. So how is it? And you have to also notice the symbol in between. It is nothing but AB, or it is nothing but A dot B, and this is A plus B. So whenever there is a dot, the inputs A and B should be connected in series. Whenever there is a plus, they should be connected in parallel. They should be connected in parallel. So how should I represent NMOS? So NMOS is represented as two inputs A and B in series, which I'll show here. So A and B is what I have to show. I'll immediately show the inputs A and B. This is what I have shown. How do you say they are in series? You have to show the terminals. Always we know that source of NMOS is connected to ground. Source of PMOS is connected to VDD. Now this is your NMOS. So this is your ground. Therefore this becomes your source. What is the leftover terminal? Drain. So this is one connection. Next, when they are in series, what would be this terminal? Source. What would be this? This would be your drain. So they drain source. This forms a series connection. So this is your NMOS. And since one is represented in PMOS, I have the representation as parallel combination A and B in parallel, number 1. Or else this itself you complement. If A and B in NMOS are in series, then in PMOS they are complementary, they should be in parallel. So how do we write the parallel combination? Parallel combination is written like this. So A and B of P type are in parallel. And one more thing, please notice, this is the output. Y is equal to AB bar. Because our NAND gate, right? A is equal to AB bar. Therefore, this is your output. If one terminal is drain, always the output is, okay, make a note, output is taken always at the drain junction. Therefore, this is your drain. They are connected in parallel. Therefore, there are two drains and drain. This is where we take our output contact. Obviously, which is the left out terminal? Source and source. So this is how this is called as a CMOS, combination of PMOS and NMOS, called as a CMOS NAND. We have to check the truth table. And one more thing, your output Y is equal to A, B bar, NAND gate. What is the equivalent representation of your output? The output is in logic high, logic low, NAND. The output is in logic low because there is a bar. If there is the output representation in logic low, the inputs should be represented as logic high. Therefore, we will have to show it as A and B itself. Next example, if I have y is equal to AB AND gate, the output is represented in logic high. So this is a representation of logic high because there is no bar here. Then the inputs are represented as A bar, B bar, A bar, B bar. Anyhow, we are not discussing that right now. I am just giving you a note of this. So the output here is represented in logic low. Therefore, the input should be represented as A and B. Now we will understand. So what is the conclusion? 2n in series and 2p in parallel. I will draw the diagram like this, which is the skeletal representation. We had one device here, one device here. We had two devices in series. This was our output. Since y is equal to AB bar, the inputs were represented as high A and B. A and B. Now we have the truth table. Justify truth table when the inputs were 0 and 0, 1, 0 and 1, 1, 1 and 0, 1, 1 and 1, it was 0. So when A is equal to 0, this is PMOS. So 0 bar, it is 1, it is high. Similarly, B is 0, since it is PMOS, there is a bubble, therefore this is also high. A is 0, open circuit, B is 0, open circuit. And this is from high potential to low potential. So the current tries to flow in any of this direction. So the current flow is shown like this. Either it can take a path like this, or it can take a path like this. So in either way, what is the logic present at y? It is high. So y in turn is equal to high, and the first condition is satisfied. Let us now go on with the second condition. So let us go on with the second condition. What is the second condition? When A is equal to when A is equal to 0, 0 bar is high. 0 bar is high. B is equal to 1, 1 bar is 0. 1 bar is 0, high. So what is the logic present at Y? Either it can take this path, it encounters an open circuit, no path. There is another alternate parallel path. Still, what is the logic present at Y? 1. This is also true. Obviously, the next condition also will be true. Last condition, when both the inputs are 1 and 1. When the input is 1 in PMOS, 1 bar is high. 1 bar is high closed. B is 1, 1 bar is when A is 1, 1 bar is 0. When A is 1, they are 0, 0. And when A is 1, this is also a short. This is also a short. And this is also a short. A and 1. Therefore, what happens? It encounters an open circuit, no current flow. Here also no current flow. So what is the logic present? Y is equal. Therefore, that circuit, what I have shown in the earlier diagram, can now be called as a CMOS NAND gate. So, then we start with the stick diagram. So, to initially do the stick diagram, you have two metal lines. So, the two metal lines are blue in color. Next we have the demarcation line. So you have to represent PMOS in the pull-up region, P and NMOS in the pull-down region. So this is also called as pull-up region, meant for PMOS, and in the pull-down you have NMOS. So this is for NMOS, which is in the pull-down region. And the next step is this is the first step. Second step, only poly can cross the demarcation line. So poly can cross the demarcation line. Poly means it is your input. So what are the inputs in our case? The two inputs are A and B. So the two inputs are A and B. I am showing this as poly is nothing but your gate to A and B. Next I have to show the diffusions. So normally in stick diagram the color code for P diffusion is yellow. So this is P diffusion, and the intersecting region, whenever a poly overlaps on a diffusion, a transistor is created. So for your reference I'll just show this becomes your transistor. So this actually is your transistor. For your reference I have shown this. Next, green is for NMOS. So similarly, green I am going to have the diffusion for NMOS. So we have now 4 transistors, and the PMOS transistors are connected in parallel. So what do you mean by parallel? Sources are connected together, drains are connected together. So normally the connection is shown in blue color. So if I call this as source, initially to identify, you can name them. You can name them. So I refer this as source, I refer this as drain, I refer this as drain, I refer this as source. For some reason I made this. Either you can name it as source, drain, however is convenient for you. I'll take this as source, drain, source, drain, no matter. You can have, so either side of the junction you have source and drain terminal, and this becomes your gate. Using metal lines you have to do the connection. So the metal line I have chosen here is blue color. What was the first connection? Source of A, or if you go back to your scheme, in your schematic representation, A and B both are connected in parallel. So source of A as well as source of B, they are connected, and this becomes your contact. This becomes your contact. Similarly, drain and drain are shorted together. Done. So this shows the parallel combination. Next, either A or B, one of them is so connected to the source. I am not able to get the schematic. So source is connected here. Next, drain is connected to source. This is where is your output. So drag this line, take a loop, and this becomes your output. This is your Y. So this is the schematic representation of an NAND gate. How do we do it in a layout representation? So two parallel lines which represents metal lines. And what is the color coding of metal? Color coding rather than that, we will have hatchings. So two types of color hatchings are shown. This is also a metal representation, vertical, but as for our syllabus, our dimensions are changed. It is 4 lambda thickness, so parallel lines. This is how you have to draw. Next you have demarcation line. Next comes polysilicon. So for polysilicon you have to show the representation with this kind of hatchings. Next again you have one more polysilicon. These are the hatchings. Once the polysilicon is done, you have the P diffusion, faraway spacings. So these are the different hatchings. Next, this is your N, close hatchings. This is your N, close hatchings. Fine. Now you can call this as A. As we have called here, we can call this as B. Next, using the metal lines. So use the metal line to short here and form a contact. This is shorted here with the help of a metal line. This is where we are going to pull out the lead for the output. Then source of this is connected. Fine. This source is also connected. This is where you have source connected. And so two sources are shorted and they are connected. They are in parallel. Therefore, this is also done. Next, you take a metal and take an overlap and pull it down. Take a metal, take an overlap and pull it down. This forms your junction. So this becomes your contact, in other words, which is nothing but your Y. So this is the layout representation for NAND gate.